Okay, so I'm going to record. I have started recording the video, so you can also watch it later if you want. Anyone, any questions before I about? So remember, I'm going to lecture till about 5:15. Maybe we'll take a tiny break. And I'm going to write here. And so later, I may even scan these sheets and send it to you. Any questions? So we completed the probability part. And again, all those ideas will come back during the second half. Sushant, how many students?
49.
All right, so at 5:15, I'll stop and you will, if you check your email, you will have an exam and you do it and upload it to the mini test number 1 folder within half an hour. And so we will have one such test every week. So let me start this. Before that, let me just start do a small probability problem. So suppose you have a large area and whatever, maybe right now the way the disease spreads or something, let's say is locally Poisson. What that means is in each of these areas, whatever is happening, number of incidents, remember Poisson is probability of x equal to k is e raised to minus lambda k over k factorial. So what I'm trying to say is that each of these may have a different lambda. So obviously the lambda is changing. So lambda is also a random variable. So the question is, remember this is only over, I'm going to call it x1. This random variable is here. So x1 represents whatever is happening in a small region. Similarly here x2, x3, etc. So if you, so the globally means we want the total x equal to k is what is the probability of x equal to k. So I hope you understand what I'm trying. So this is local behavior, each place. Each of these places, it is local behavior. We want to find out global behavior. So if you are not in this course, you'll say, okay, locally Poisson, everything is Poisson. That is not true, as I'm going to show. In other words, the local behavior, the moral of the story here is the local behavior here may not exhibit the global behavior. So let's go into global behavior. So globally, so I hope you see what is going on. So the whole point is in the previous slide, these lambdas are varying. So we are going to consider the lambda to be a random variable. And so the lambda has a distribution. And I'm going to say that it's an exponential distribution with the parameter mu. You can try out various distributions. I'm just going to do this. So if lambda is exponential, then the limits go from 0 to infinity. So we wrote this one. So this is e raised to minus lambda to the power xi equal to k, not lambda, xi equal to k. The xi happens to be Poisson with the parameter lambda, but the lambda itself is random. I hope you understand. This lambda is representing the local behavior. Lambda is for any one region, but the lambda varies all over. So this is the local behavior. I'm going to multiply by the density function of lambda. So this is exponential. So locally Poisson. So 0 to infinity. Remember, the integration is over lambda. So I'm going to collect all the lambda terms. 1 over k factorial goes outside. E raised to minus 1 plus mu multiplied by lambda. Mu also goes outside. Lambda to the power k over k d lambda. Already k factorial I picked up. So I'm going to put 1 plus mu multiplied by u, lambda to be u. And so you get d lambda equal to du divided by 1 plus mu. So if you substitute here, and this is going to be mu over k factorial integral 0 to infinity e raised to minus, the whole thing is u. Then lambda is, look at here, lambda is going to be u over 1 plus lambda. So I'm going to substitute, here you have lambda k. So that's u to the power k over 1 plus lambda to the power k. D lambda is du divided by 1 plus lambda. So this big, that's a 1 plus mu, I'm sorry. So that goes outside, not 1 plus lambda, 1 plus mu. So you get mu divided by 1 plus mu to the power k plus 1. K factorial 0 to infinity e raised to minus u, u raised to k du. Anybody knows what's the value of this integral? We have done this several times. Anyone? Hello? You can do this by parts. If you put u to the power k here, you can easily see. Anyone remembers the value of this integral?
It's just u to the power of k.
Now remember, you are integrating out k. How can it be? So put u to the power k here.
Be k factorial.
Yeah, it turns out to be k factorial. So the k factorial will cancel with this k factorial here. So you'll get the answer to be this. So we have probability of x equal to k. Turns out to be from the previous sheet mu over 1 plus mu to the power k plus 1. I'm going to write it like this. So if you call this to be p, you can see q is 1 minus p. That's 1 over 1 minus mu over 1 plus mu. That will be 1 over 1 plus mu. In other words, this is q. So I hope you see that this is q to the power k. Pq to the power k. K is 0, 1, 2, 3, etc. Anybody, what is this distribution? Anyone? A probability of x equal to k is pq to the power k. What is that? We have seen this. Huh?
Geometric.
Yeah, geometric. So we have a theorem. Locally Poisson, but globally it is certainly not Poisson. But globally geometric here. I mean, provided the Poisson parameter is, so locally Poisson means the Poisson parameter is random. Provided the Poisson parameter varies as exponential. So you see, you can, this is certainly beyond common sense. Without knowing this course, it's very hard to believe that if you have local Poisson behavior, if you look at the aggregate, that will look like, what is it, geometric. Why should the whole behavior be geometric? That's because the depending on the variation of lambda, in which here we assumed it to be exponential, we got geometric. If you assume the lambda is something else, you will get some other result. That's what it is. Any questions? I mean, this was just a warm-up to show you the power of the things you have studied. So I'm going to go to stochastic processes. How many are there, Sushant?
53.
55, I see 55.
Yeah, but two of us are you and me, so 53.
Okay. At some point you can leave. You come back at around 5 o'clock, 5:15, or you can stay here, whatever.
Yeah.
Professor?
Yeah.
Is there a way to turn off the autofocus on the camera? Because it keeps zooming in and out.
Yeah, you're right. So what should I do? Let's see. Is this focused or no?
No, it's unfocused. That's. Oh.
Yeah, this the thing is. So let me see how to. Oh yeah, I'm going to put autofocus on manual. Is this good?
It's still blurry.
Still blurry?
Yeah. That's pretty good.
Better, right?
Yeah.
It's going to become blurry. Sorry, this is a new problem now. I need to figure out a way to stop it here.
Professor, you can try putting the camera a bit back and then turning on the autofocus.
Your autofocus, I have two options here. S and C. S is what?
S will only focus once and C will be continuous.
Yeah, which is what I'm trying. Still focused or not focused?
That's still pretty out of focus, Professor.
Yeah. Well, I'm going to continue. See if I could know how to stop it here. So we studied a random variable. A random variable x has a density function. And the meaning of the density function is that if you take some, it's a function of x, it's a non-negative function. Area under it is 1. And the Physical meaning is that probability that the random variable takes values between x1 and x2. In other words, when you do an experiment, the fact that it will be somewhere in this range, this probability between x1 and x2 is simply given by the area under the density function. So that's the meaning of the let's see this one. That's the meaning of the density function. So this is one random variable. Now what we are going to do is we are going to bring in time. So we have, remember in the random variable case, you have just the random realization. Whereas here you have two variables, both the time and something to represent the randomness. So remember, previously we were just dealing with the randomness. Now we bring in the time also. So because it is time, so you get a collection waveforms, one set of waveform. So this is to represent the phenomenon, because the phenomenon is evolving with respect to time. But it is not just one waveform, you have a collection of waveforms. So of course, what are these different waveforms? This waveform may be for a particular value of psi1. This may be for another value of psi2. This may be another value of psi n, etc. So in other words, in this direction, in the y direction, it is the variable is psi, and in the x direction, it is time. So randomness here, randomness along the y-axis, and time along the x-axis. So you will see that if you think as a second, you will see that if I freeze time to t equal to some t naught, what do you see here? See, you see one value, you see another value depending on the random value, you see another value, etc. So you can see the behavior here is the same as this. In other words, you see a random variable here. So the simplest way to characterize a stochastic process is that for fixed time, the process behaves like a random variable. The process behaves like a, so you take, so let's call this is t1. So I can call this to be x1 equal to x of t1. I take some other time instant t2. I get this will be the value of the, I freeze time to x of t2. So I get a random variable t2 because there's a second variable here. That's so this is x of t1 means x of t1 comma psi. So a stochastic process is a collection of waveforms for any fixed t. The process x of t1 comma c. Remember, then this is the free variable. T is fixed, and so I'm going. So we can call this to be x1. So x1 behaves like a random variable. That's the key. So I hope you understand how we bring in the time is if you fix the time. If you fix the time, then you are going to see a random variable. If you fix another time, you are going to see two random variables. Now you can see where I am going. If I fix another time instant, so I'll draw it here. So time instant, this is T1, T2, T3, etc. Let's say Tn. So you get random variables x1, x2, etc., xn. So, you know, each random variable has a density function, you can say. And this random variable is corresponding to time t1. So we could probably write it like this. So you have x1. X1 is the stochastic process evaluated at the time t1 corresponding to all the realizations. So x1 will have a density function, which I'm going to denote it as this way. So this is the address which random variable we are referring to. And this is, it's a function of time. So if you, and say same thing with x of t. So if you take two random variables from what we have learned, this is where what we have learned comes in. You get a joint density function, which what must be two variable, but it is also functions of t1 and t2, etc. So the question is, you can see it's a mess. It's a collection of waveforms. Question is, how do you characterize them? So characterization of stochastic processes. So it may be countably infinite or uncountable. In any case, it's an infinite collection of random variables. The stochastic process is an infinite collection of random variables. So the first order characterization is only deal with one random variable. That's what, so in other words, we define a random variable x, x1 to be x at the time t1 and psi. So x1 means x1 of psi, of course. And that will have, this we will have a density function, x comma t1. So this is the first order characterization. And if you have a random variable, we have already learned the simple, what is the simplest parameter that you can describe a random variable with? One parameter. Anyone? Hello? If you have a random variable, how do you describe it using one parameter? Anybody? I mean, go back to what we learned about one random variable. What were the characterizations for one random variable? Hello? Remember, what I meant was towards the fifth lecture or something, we went through characterization of random variable. We instead of density function, we started characterizing it through a few other parameters. Anyone remembers?
Mean, variance.
Mean and variance.
Yeah, mean and variance. So the easiest one here is mean. So we can define the mean of as x of t1, or we can simply say this is the mean of the stochastic process. So what this means is, this mean is referring to time t x t. So that will be from here. At any time, the random variable, the process behaves like a random variable with this density function. So if I put a t here, this will be t. So the mean will be fx of x comma t dx. Notice that x integrates depending on whatever is the thing. So you will get it to be a function of, I hope you see that this will be a function of t because there is a t here.
Professor?
Yeah.
So what does the sign mean there?
What does what mean?
Like you write the x, t, comma, sign. What does the sign mean there?
Yeah, so as I said, so if you go back here, a regular way, let's say sine omega t, there's only one waveform, right? Generally, yes. A function only has one waveform. Here, look at this. I drew several waveforms on top of each other. So each of these waveforms correspond to random values. For example, if you're tossing a dice, there are 6 outcomes. So one way to generate a stochastic process will be, let's say, some waveform, let's say a square waveform, periodic waveform. But there is also a second parameter which depends on the whatever is the outcome on a outcome of the tossing a dice. So let's say the simplest example is this one. Let's say this is, consider this stochastic process. Oh, let's say this is a very simple example. I hope you can read it. X of t is cos omega naught t plus. If this was not there, we know it's a nice waveform, cos omega naught t plus phi. Phi is the result of tossing a coin. So when you toss a coin, you are going to get head or a tail. So let's say you assign the values 1 or 0. So if this is 0, you will get cosine, which is this waveform. If it is, this is the waveform corresponding to the tail. If it is head, let's say this I multiply by pi. So this will be pi multiplied by that. Then this will go like this. So the whole point is, since there is a randomness here, we wouldn't know which waveform would be the appropriate one, because these are 2 realizations depending on this outcome. So this is random. Whether it is this one is going to happen, this one is going to happen, we don't know. It depends on this outcome. So another example would be, let's say, cos omega naught t plus phi. This is a better example where phi is uniform between minus pi to pi. So this is a random variable. There is nothing random here. So because of the phi, this is another. This is a stochastic process, because depending on the value of the phase, waveform will start with some phase. So whatever is this phase will depend on this. This value will be cos phi, right? When t equal to 0, this is cos phi. If phi is 0, it will start like this. If phi is pi by 2, then it will start from 0, etc. So coming back to this. This is what the psi represents. Psi is the value of the random realization. Whatever is the randomness, whatever its value, it may be through a random variable, or it may be more complicated. So in any case, so it's a collection of waveforms. Unlike, remember, in 611, etc., you study one waveform going into a system, whereas here it could be one among the many waveforms. So the psi is a representation of those many waveforms. I hope that's clear. So coming back to this, so the whole somebody's playing music. So the mean of the process, notice that this mean is, unlike the random variable, mean is a function of t. And this is the first order. This is the first order density function. And this is just a property, the mean. So remember, the whole point is, how do you characterize the stochastic processes?
Professor?
Yeah.
For any point of time, the distribution is now the same?
Yeah, that's so. Look at here. You have, if you look at this, look at the behavior. If you look at this, you will get one random variable. And because it is a time instant t1, its density function will also be a function of t. So whatever is the shape of the density function will depend on t. If you go to some other time instant t2, you get a different random variable whose density function is t2. So that density function may look completely different. So you are absolutely right. These two density functions doesn't have to be the same in general. Understand?
Okay, thank you.
And you can see why, because the waveform may have different properties, the values, etc., may be different, etc. So in general, and if you take some other time instant T3, you will get a different density function x comma T3. Excuse me. So the variable, this is the variable x. The variable x is the same, but you can see the probabilities, all this may be different depending on the process. So different time instance we will have. So remember, how many random variables can you create for different, if you pick up different time instance, how many random variables can you create? Anybody?
Infinite.
Infinite.
Yeah, infinite. And each of those random variables will have, could have different density functions. Now, I only dealt with one random variable. We can deal with the two random variables. How do you characterize two random variables? Anybody? If you have two random variables together, what is the best way to characterize them?
Joint density.
Right. So if you have x1, which is x of t1 comma psi, you have the density function fx1 x comma t1. If you have two random variables x1 and x2, so then you remember x1 is x of t1 comma psi1 psi, x2 is t2 comma psi, and then you have their joint density function x1 x2 t1 comma t2. So if you have three random variables x1 x2 x3, what do you get? Anybody? Anyone? 3, what do you get? You have their joint characteristic function, right? I mean, joint density function of three random variables corresponding to time instance T1, T2, T3. And if similarly, if you have n random variables, x1, x2, etc., xn, how do you characterize the n random variables? Anyone? Hello?
X from 1 to n and t from 1 to n.
Yeah. So what does this density function mean? Remember, we only did two of them in the class, but it's easy to generalize. So if you have the joint density function of x1, x2, x3, how do you get the joint density function of x1 and x2? Anyone? If you have this
Take
one,
the integration with respect to x3.
Exactly, right. Similarly, if you have this one, to get x1, you integrate out x2. So this is the joint density function of all n of them. From here, you can get all the previous ones. Yes? Right? And similarly, we can also define the joint distribution function. x1 less than x1, x2 less than x2, etc., xn less than xn. But we also have to say that x1 corresponds to t1, t2, etc., tn. So I forgot to add that here, this will always be functions of t1, t2, etc., tn. So So you create these random variables at time instance t1, t2, etc., tn. Then the joint density function of these random variables gives you the nth order character. This is the nth order characterization of the stochastic process. So let me ask you this question: how far down can you go this way? Anyone? Hello. What I am asking is, you can describe the density function of one random variable, two of them, three of them, n of them. Then what? How far down can you go?
Till infinite.
What?
Till infinite.
Yeah, so you can have infinite characterization. Because for any value of it, so you can see this is really hopeless, but that's the complete characterization of, so n can go from, what I'm trying to say is, n can go from 1, 2, 3, n, etc., all the way to infinity. But in this course, we will only deal with the first and second order characterization. That's all usually people do. So first order characterization means the density function is this. Second order characterization means you take two random variables and look at their joint density functions. So you understand what I wrote here? I said first order and second order characterization. Then I said the strict sense characterization. Like, oh, I guess you can't see. A strict sense characterization. Why I call it strict sense is because you are dealing with the density functions. There is nothing more fundamental than the density function. That's why we call it strict sense characterization. So let me rewrite it here. So this is the first order characterization. And the second order is you take two. So I hope you see the picture. You have some time instant T1. You have some other time instant T1. We want to know the behavior of these joined, these random variables, joint behavior. So that joint behavior will be through this joint density function. So second order characterization will be two random variables, one at T1, other one at T2. And the joint density function is x1, x2, T1, comma, T2. So this is this second order strict characterization. So essentially we are trying to study the random variable by itself and also their joint behavior. We can take three of them, but that's all too much. We will only deal with at the most what is the joint characterization of two random variables. So look at this, as I said, if you have, so this is the strict sense characterization. And there's also something else called a wide sense characterization. So so look here, the first order strict sense characterization is using this density function. From this density function, we can create one property. Property is the mean. So this is the mean of the stochastic process. Similarly, let me ask you let me ask you guys, see whether you can recall from what we have learned. So here we have the second order characterization. That is to study the joint behavior between the random variable here and random variable here. So do you recall a property or that we derived to describe the behavior between two random variables, x and y? Anyone?
Covariance.
All right, so we want to bring in, and what's the definition of covariance? Anyone?
It's a correlation multiplied by their standard deviations.
Right, and how do you define the, or how do you define the covariance? It's expected value of what? Expected value of xy minus mu, right?
Yes, yeah.
All right, so similarly here, we defined one property. What we want is, we want to derive another variable which will describe the joint behavior. So we are going to look at something like this. So let me, what is this? You have seen this obviously. If you call this to be X, this to be Y, what is this one? If this is X and this is Y, then this is expected value of XY. So what's the definition of expected value of XY? Anyone?
Oh,
XY times.
like
Yeah, I'm going to call this X1 and X2 because that's what it is.
X1.
X1, X2, and the joint density function of both.
Yeah, but look at the previous sheet. Look at the joint density function. Where is it? Here. Joint density function is a function of X1, X2, and also where these random variables were located, which type. So T1 and T2. So notice this will be X1, X2, T1, T2. So I hope you see that when you do the integration dx1, dx2 will go away. Then you will get this to be a function of T1 and T2. So generally this is the notation. We use R. So this is like a covariance or correlation. So the standard, the nomenclature used for this is autocorrelation function. This is not exactly a correlation, but that's the word used. Why it is a function? It's a function of T1 and T2. That's what the whole point. Remember, for the random variables, the correlation came out to be a number, whereas here it's a function of T1 and T2 separately. So I hope you understand. So this is Strickson's characterization, first order and second order. This is sort of the wide sense characterization, wide or sloppy, or wide means what I told you, which is through property. So first property is mean. The second property is expected value of so again, expected value of x of t is what? Integral x fxx comma t dx. And expected value, second property is t1 xt1 multiplied by xt2 star. So this is going to be double integral x1 x2 star, the density function. Any questions on the properties?
What does the star indicate here?
Star is complex conjugation, right? And I will show you why this is important in a second. So this is known as the autocorrelation function. So now next one is mean. You are reasonably familiar. So we will use this expression for the mean. This is our notation. This is the autocorrelation function. Star is because, let me put a T1 equal to T2. So if I put a T1 equal to T2, this becomes expected value of xt squared or T1 squared. You are familiar with this. If you take a waveform, take the absolute value squared and take the expectation value, what do you call this in electrical engineering? Anyone? Suppose this is voltage. Square of the voltage, expectation is average. So what do you call this?
It's power.
Average power.
Yeah.
Mean squared power. Mean, this is mean squared, whatever is this quantity, power or, so this is like an RMS value. Look at that. If I didn't have this star here, when I put T1 equal to T2, this will become only xt1. And if the waveform is complex, that's not very good. So if you consider the processes where the waveform could be complex, autocorrelation is defined with a star here. Of course, if there is no complex, this will be xt1 multiplied by xt2. Is that clear? Hello? If x of t is real, then r of t1 comma t2 is simply expected value of xt1 multiplied by xt2. There is no star here. So this is the power, you're right. Any questions? So in general, there will be a star here. Now I need to, the autocorrelation function is where I need to spend some time, and that is what we may do today. We will see. So your homework is also about autocorrelation functions, because that's the way we are going to characterize the stochastic processes. Generally, a stochastic process, the first thing we need to find out is so to characterize a stochastic process, remember, you can go this way, but the trouble is then you need the density functions. Usually these things are not available. All you have is some data. So generally what we would be happier is, or we'll settle for, is the mean and the autocorrelation function. So you need to know how to compute the mean and autocorrelation. More important, you need to know what are the properties of autocorrelation functions. So again, R of Rxx T1 comma T2 is expected value of xt1 multiplied by xt2 star. Remember, this means double integral x1, x2, joint density function of x1 and x2. But x1 corresponds to time t1, x2 corresponds to t2, dx1, dx2. So the first property is that
Professor, so is this similar to like finding the covariance, but within a random variable itself?
Yeah, covariance is for one random variable, right? I'm sorry, covariance is for two random variables, expected value of xy minus mu x mu y, right?
Yes.
Yeah, so this is very close to that, right? Look at here. What is covariance of x comma y? Expected value of xy minus mu x mu y. So here x is x1, this is x2. So then this will be expected value of xt1. And let's say in the complex case, this is xt2 star. So this portion is what we are calling the autocorrelation function. You understand?
Yes.
Yeah. So anybody has heard this term? First property is that autocorrelation function is a non-negative definite function. Anyone? What does that mean? Anyone?
It's greater than 0, like strictly greater than 0. And
there are two variables. Look at the autocorrelation function. What are the variables of it?
x1, x2.
Look again. x1 and x2 are the addresses, right? See, look at here. Where is x1? x1 got integrated out. So why is it x1 and x2?
Okay.
So what is it? If you integrate out x1 and x2, what is it remaining here?
T1, T2.
Yeah, that's why I wrote it here, T1 and T2. This is only an address. Why is it called, look at here, I didn't write x1, x2. Notation is you write xx, saying that's why it is called auto. We are dealing with the covariance of the same process, not a different process. Later you can have x of T1 and y of T2, a different process. That will be cross correlation. This is autocorrelation. So anybody, what does this mean, non-negative definite? Oh, one of you must have.
It's like positive definite.
Okay, what does positive definite mean? Anyone?
I think I just know from matrix.
Okay, what is it?
It's like x times a matrix times x transpose should be greater than 0. Then we will call
Oh, very good. See, all of you, I see, how many are you? 62 students are there. All of you are graduate students or 60 students. So you should know this property. So I'm going to explain it to you what it means. What does this mean? And maybe next Saturday or something, I'll give you a little bit matrix algebra course. So see, you put different values of T1 here. What I'm trying to say is, see, you have two variables. T1 goes this way. So let's say call it T1, T2, etc. up to Tn. And T1 and T2 goes this way. In other words, the time variables are, take the variables T1, T2, T3, etc., Tn. You take arbitrary T1, T2, etc. Then you can create here, look at this. You can create, I'm going to call R11. My notation for Rij is R of Rxx, Ti, Tj. So let me create this matrix. This will be R12, R13, etc., R1n. R21, because it's 2 here, 1 here. This is 2, 2, 2 here, 2 here. So remember, you can see that we are getting a little sophisticated here. You need all this understanding to solve the homeworks. So please follow me carefully, and also you need to do some reading. This course, you are not going to pass the rest of it by not doing any work. You need to learn something new here. So a little bit of matrix algebra. I'll try to set up a extra session maybe next coming Saturday or Sunday. Let me find out, but maybe we'll just go over matrix stuff at that point. So remember, this is a matrix I'm going to call R. What is the size of this matrix? Anyone?
N square.
What?
N by n.
N by n, right. So what he said is correct. If I multiply this matrix on the left by a vector, I'm going to multiply here by a vector X transpose. On the right, I'm going to multiply this by a vector X. In other words, X transpose X. X transpose Rx. Now, maybe we'll go over this next week. You go home and try to multiply. So let me call the vector X to be, where is it? X is some arbitrary vector, X1, X2. Or a vector. I don't want to confuse this X with, so let me write it. So I have a matrix R. These entries are R11, R12, etc., R1n, R21, R22, etc., R2n, Rn1, etc., Rn. So I'm going to multiply by a vector A star here, A here, A star here, A here. The vector A is column vector, some A1, A2, etc. A. Now, maybe we'll go over Saturday. If you expand this, you will come out to be AI, Rij, Aj star. You just need to expand this. So A star is like this, R is here, A is you bring it here, and then you the cross multiply, you can show that it turns out to be. So if R is positive, non-negative definite means this quantity is non-negative for any vector A. That's the. So I'm going to show that our R has this property. That's what I want to show. R is non-negative means A transpose. So let me take, remember R is what? R is expected. Rij is expected value of xti multiplied by xtj star. So I'm going to take this double summation. So I hope you see that, as I said, you have to see how these problems are solved. Then you try to solve the problem similarly. I am creating a vector. Look at what I am doing. I take these random variables. This is x1, x2, and I stack them up. So this is a random vector. because all the elements are random variables. Now I take another A. A is A1, A2. These are just arbitrary constants. Then I'm going to take, define A transpose X. That means, I hope you can see, A transpose means you tilt it and multiply that. That will be AI X of Ti. Anybody, what will be the nature of Y? Anyone? Y will be what? These are random variables, so Y will be?
Random variable.
Or Y will be because it's a sum of other random variables. So Y is a random variable. Let's say they are zero min. Let's say expected value of Xi is 0. So expected value of Y is 0. It doesn't have to be. Then I'm going to do expected value of Y squared. This is the key. Actually, you don't even need that. Expected value of Y. So I hope I'll do it here. So Y is summation AI X of Ti. I'm going to do expected value of Y squared. That's going to be Y squared multiplied by Fy dy. Y squared is positive, this is positive. So this will be what? This will be negative or positive? This quantity, expected value of Y squared. Anyone?
Positive.
Yeah, it is non-negative, right? Now for Y, let me substitute it from here. So this is also equal to expected value of a summation AI X of Ti squared, I equal to 1 through n. So that means expected value of summation AI X of Ti multiplied by summation, this is on I, Aj X of Tj, right? Star is here because expected value of Y squared means expected value of Y multiplied by Y star. In the first Y I use, this variable is arbitrary. Here I used I, here I used J. Now let me collect the two summations outside. And A's are constant, so this is AI, Aj. Then expected value of Xti, Xtj star. But you can see this is your R of Ij. So we got this summation AI, Aj star, or Ti, comma Tj is always non-negative. This is, if you want in matrix notation, you can write it like this. So any R, any R has this property. We didn't go through, remember, so far I have not discussed any particular example. So this is true with any R. Any questions? So remember, you will say, or it doesn't matter. This matters because we'll keep coming back to it.
Professor, I have a question.
Yeah.
So you make the when you make the inequality, then should we include the equal? Maybe it can be 0 actually. I mean, is strictly greater than
So
0.
some cases, for some values of AI, I'll go to, all we can say at this point is inequality, because that means for some value it can be equal to 0. It can be equal. We'll come to that. So if it is strictly positive, then it is positive definite. So far, we are only able to say that it's non-negative definite. Okay. So the first property is R of T1 comma T2 is non-negative definite. Now hold on, I need to plug in this into somewhere. Hold on. Look at its definition. The second property is this one. Rxx t1 comma t2 is by definition expected value of xt1 xt2 star. So I'm going to pull out the star outside. If I pull the star outside, this becomes xt1 star xt2 because I pull the star here. Double star is back. But this, if I rewrite, I can write this as xt2 xt1 star. I just flip the terms, star here. But this is the definition of Rxx t2 comma t1. So we get this property. So Rxx t1 comma t2 is Rxx t2 comma t1 star. Okay, this is the second property. Any questions? Otherwise, I'm going to move on. I'm going to show you some examples of stochastic processes. Anybody? Any other questions? And of course, the expected value of x of t squared is Rxx t comma t, right? So that's the third property. The average power of the stochastic process is given by Rxx evaluated at t comma t.
Professor?
Yeah.
In the property number 2, so how does the xt1 transpose change to xt2?
No, remember this is, I can 2 multiplied by 3 is the same as 3 multiplied by 2. I just put this number in the first and this number at the second.
Oh, yeah. Sorry.
And then by definition, here the first variable comes here, the second variable comes here with a star. So the first variable comes here, second variable with the star comes here. Yes?
Yes.
Let me give you 3 examples. So the first example is a simple one, and this will help you to do the homework. So this is a stochastic process. So I hope you are listening carefully because this is not an easy part, all the stochastic process. So this is a stochastic process because this is where the randomness is. So what that means is I have no idea about the phase. Depending on the phase, I'll get a new waveform. So you can see there are an infinite set of waveforms depending on the value of phi. So the question is, what is its mean and variance? A mean and autocorrelation function. So the mean is the mean of this. So I'll show you how to do this. Anybody, what do you do now to find out the mean? We can expand this. So if you expand the term, this will be cos omega naught t cos phi minus sin omega naught t sin phi. Expectation goes inside. So this is cos omega naught t, expected value of cos phi. This is where the previous course helps. Sin omega naught t, expected value of sin phi. Anybody, what is the expected value of, how do you find this quantity? Phi is uniform 0 to 2 pi. So how do you find this? Integral? The function multiplied by density function. So which is what I've done. And what is this value? Anyone? If you do it
0.
mentally? Yeah, same thing here. The integral sin phi multiplied by 1 over 2 pi 0. So the mean is 0. So let's find the autocorrelation function. So that's going to be expected value of, I'll do it on a different sheet. So autocorrelation function is expected value of cos omega naught t1 plus phi cos omega naught t2 plus phi. So I get, this is cos A cos B. So I can expand half of cos A plus B. Well, is it or A minus B first? I forget now. What is it? A minus B, right? A minus B. So that will be, or B minus, either way, cos omega naught T1 minus T2. Then A plus B. So that's omega naught T1 plus T2 plus 2 phi. So look at this. This term is a constant. There is no phi. So that goes outside. Or you can write either way, T2 minus T1. Plus here again, we do the same thing. Plus the expected value of cos omega naught T1 plus T2 plus 2 phi. And again, as before, you expand this into two terms. This is, if I call this to be A, this is cos A cos 2 phi minus sine A sine 2 phi. And you take the expectation over sine 2 phi and cos 2 phi, will get 0 by the same argument. So this will be the autocorrelation function of that process. That was easy. So let me do a harder example. So this is comes in queuing theory. It's a classic problem. So I can for the today rest of the class I can talk about Poisson process, but at least I'll give you some introduction. So Poisson process means things keep arriving, things are happening, like whatever is happening now. As time progresses in the city, somebody is getting the coronavirus, right? So you count. It's a counting process. You take some. So what if somewhere there is an origin, you put to some t and see how many arrivals are then. This is the number of arrivals. And this is what we are going to call x of t. I hope it is clear to you. X of t means the number of arrivals here. So you count it 1, 2, 3 up to k. So if this is the kth arrival, then you say x of t is equal to k. So Poisson process is going to be defined by two properties. Definition. You have two properties. So this means what? Anybody? According to this notation, what does this mean? N of T1 comma T2 means?
Number of arrival between T1 and T2.
Right, number of arrivals in T1 to T2. So what is the duration here from T1 to T2? Anybody?
T2 minus T1.
T2 minus T1, right? From larger time. So not the number. This means the number of arrivals in T1 minus T2 is a Poisson random variable with the parameter proportional to the duration. That's so we can write it this way. The parameter is not only depends on lambda, but it also depends on the duration. So if this duration is tau is T2 minus T1, then this is lambda tau. And the second property is if two intervals are non-overlapping. See, if you have an interval here, if you have an interval here and you have an interval here, if this is T1, T2, T3, T4, if two intervals are non-overlapping, then the corresponding Poisson random variables NT1, T2 and T3, T4 are independent. Anybody, what does it mean, independent? When do you call two random variables to be independent? Anyone? Hello?
The mean of their multiplication is the multiplication of their mean.
Mean? Again, think about it. The independence is not defined through mean. How do
the
you define
probability of
Join to, yeah. Join to probability.
yeah, the probability of n1 times the probability of n2 is equal to the probability of n1 and n2.
Yeah, not probability. The joint density function is the product of the molecules, right?
Covariance is 0.
What?
If two random variables have like covariance is 0, then we
I
can
know,
say
but that
they're
is not the
independent.
definition of, that's all properties, right? When do you call two random variables to be independent? Covariance can be 0, but still they don't have to be independent, right?
Yeah, that's true.
So when do you call two random variables to be independent?
The joint density function is equal to the
Product of each other.
product. Yeah.
Right, right.
Yeah.
So that's, so you understand. So we call a process to be Poisson if these two properties are satisfied. So you have to sort of understand what these properties are. So it's like arrivals. See, you look at a bus station. If you keep looking there, people will be arriving there to waiting for the bus. So so you pick up some time. Let's say you start looking at 4 o'clock. Maybe 4:05 somebody comes in, 4:08 somebody comes in. So that is sometime you can model that as a Poisson process. So the number of arrivals. So x of t is the number of arrivals from 0 to t. So we need the expected value of x of t. This is the, remember, this is a Poisson process with the parameter lambda t. So this is n of 0 t. So if x of t is a Poisson with parameter lambda t, what is its mean? Anyone?
Lambda t.
Lambda t, that's good. And its variance is?
Lambda t.
All right. So expected value of x squared t is how much? Anyone?
Lambda squared t squared minus lambda t.
Yeah, because that's variance of lambda t plus expected value of x of t squared, right? Yes? Because variance is this minus this, right? Yeah, the square is here. Yes? Yes or no?
Yes.
Yes.
All right, very good. So I'm going to try, the question is, what is the autocorrelation function of a Poisson process? That's what we are trying to find out. That is not this. So autocorrelation is expected value of xt1 multiplied by xt2. I don't have to write the star because this is a counting process. Everything is real. So to do this, are these two random variables independent or dependent? Anybody? Say, let's say 0 is here, t1 is here, t2 is here. X of
Dependent.
t1, huh?
Dependent.
Because x of t1 is the number of number of arrivals here. X of 2 is the number of arrivals here. So they are dependent. These are not independent. How do you create two independent random variables from these two? Anyone? One is this, other one is?
T1 to T.
How?
Yeah. So n of 0 comma t1, and this is n of t1 comma t2, right? Yes.
Yes.
This is the same as x of t2 minus x of t1. So how about these two random variables? Anybody? X of t1 and x of t2 minus t1 are?
Independent.
I'm going to use that property. Watch what I'm going to do here. X of t1. So instead of multiplying these two, I'm going to multiply these two. I'm going to multiply with x of t2 minus x of t1. So these are independent. So I can write this as x of t1 multiplied by expected value of x of t2 minus x of t1. What is the expected value of x of t1 here? Expected value of x of t1 is, look at the first line. Anybody?
Lambda t.
T1, right?
Yeah.
What is this is also a Poisson random variable because the number of arrivals in t1 to t2. So what's the value of, this is n of t1 comma t2. What is its expected value? Anybody?
Lambda tau.
Tau is what?
T2 minus T1.
Okay, so that's good. Look at here. That's good. Now, on the other hand, let me expand this. On the other hand, I can also write this as expected value of xt1. Look at this, multiplied by xt2 minus xt1 multiplied by xt1. So that's expected value of x squared t1. What is expected value of x squared t1? It is here. What is the value? Anybody? Just read it from here. Expected value of x squared t is how much?
Lambda times t1 plus lambda times t1 squared.
Yeah, lambda times t1 plus lambda squared t1 squared, right? Yes?
Yes.
So let me, I obviously I'm running out of space here. So I have the expression rxx t1 comma t2 equals, I'm going to take everything to the other side, lambda t1 plus lambda squared t1 squared minus lambda t1 lambda t2 minus t1. So notice that if I simplify, this cancels with this. So I have lambda t1 plus lambda squared t1 t2. This is when t2 is greater than t1. What happens if t1 is greater than t2? How do we do? We don't have to do all over. If t1 is greater than t2, what happens? All we have to do is
Just
what?
switch t1 and t2.
All right, so this becomes lambda t2 plus lambda squared t2 t1, which is t1 t2. So if you want, you can write this as a lambda multiplied by minimum of t1 comma t2 plus lambda squared t1 t2. So this is the autocorrelation function of a Poisson process.
Professor, can you move to previous page? Just want to do a screenshot.
Yeah, what is that?
Yeah, thank you. Yeah, I just want to take a screen capture.
Yeah, I mean, again, I'm going to, everything is being recorded, okay? But you can take a screen capture. You got it?
Yes, thank you.
So now let me show you, as I said, I can go on and on, but I'll show you one property. So think of this as a queue, whatever. People are arriving. I'm going to generate two sub-queues. So I'm going to, the whole idea is that I pick up each queue, I'm going to pick up, so I picked up from the previous queue, I tossed a coin and picked up one. Similarly, so the way I'm going to create the two random queues is I toss a coin each time. If I get a head, I may ask this person to come here with the P. If it is Q, if I get tail, the person goes here. So you can see that's the way I created. So let me call this y of t z of t. Is everybody clear what I'm doing? From a Poisson process, I'm creating two sub-Qs. So if you want an example, suppose people are going into a bank. So if you stand outside, people are coming in at a random time instance, following a Poisson queue or Poisson process. But then you can see, oh, let me separate the male and female. So the y of t may be the males and z of t may be the females. We want to know, if you do this randomly, we want to know what is their characterization. So let's try to do that. So the way to proceed is, this is the way we are going to create yi, right? So let me go back here again. What time is it? You have a main queue. I'm creating a two sub queues. The key is randomly. This is the key. I am not asking the first person to go here or anything. Every time I toss a coin, and depending on the outcome, I'm going to ask the person to go here or go here. So this is not a deterministic queues. I'm not asking every other person to go here, etc. That's different. That's what I mean by, so if you generate two queues subsequently, then
Professor?
Yeah.
Do they have to be partitions?
What does that mean?
I mean, so the two subsets, if they're merged, they have to be the parent set?
Yeah, of course, right? Yeah. Look, a person is coming here. Look at here the way it is done. A person is coming here, like say you are standing outside. You toss a coin. Let's say you are the god. Then you toss a coin. If it is head, you ask the person, whoever is coming in, ask him to go into QA. If it is tail, you ask them to go into QB. So that's how you create two sub-Qs. But you are not arbitrarily saying that every other person goes into A, etc. You are not deciding it. A coin is deciding it. In other words, if you leave it to, if there are two options, if you leave it randomly, how the sub-Qs will be formed. That's what we are trying to see. Yes?
Okay, thank you.
Yeah. Let me see whether I remember this from my head. So look here. So I'm going to find the joint density function of these two Qs together. So I'm going to, remember, it will be a discrete output because total number of people. Let's find out the joint density function of y of t equal to m and z of t equal to n. But remember, so I'm going to substitute here for z of t equal to n. Y of t is m. That's the same as saying n equal to m plus n. I don't have space here. So probability of y of t equal to m and n of t equal to m plus n. That's the same as this. So remember, we are using probability and some arguments. Now this I can write it as y of t equal to m given n equal to m plus n. and probability of n equal to m plus n. Right? Probability of A comma B, A intersection B is the same as A given B multiplied by B. Lecture number 1. Now look what is going on. Let's try to find out this. Look here. If this n, look at here what it says. So you have to be alert. If this n is a random variable here, this n is random. But if that n is given to be m plus n, and each of them is a Bernoulli random variable, not binomial, Bernoulli. Anybody remembers if you have independent, if you add up independent Bernoulli, what do you get? Anyone? Hello? Bernoulli is what? Just a coin tossing, head or tail. So this is the number of heads in m plus n tosses. What will be that one distribution? Anyone? Each x, look at here, each xi is only 2 outcomes, 1 or 0.
So it's from 0 to n.
0 to what?
To n.
I know, but I'm saying this random variable is called Bernoulli. I did.
Oh, it's a normal distribution.
No. If you add a bunch of Bernoullis, what do you get? See, this is
Binomial?
Geometry.
What?
Binomial?
Yeah, it is binomial. Oh, it's not because look at here. I went through this. Think physically. You have to start thinking. This is the number of heads in one toss, right? Xi. Yes. See, xi. We are adding up the heads because when xi equal to head, you get p. So this is, if it is a head, it will add up. So y of t will represent the number of heads in m plus n tosses. That's going to be, so this is a binomial with n equal to m plus n and k equal to whatever we have wrote, k equal to m. Do you see this? This is the hard part. Excuse me. Should I explain this again? Hello? Or you don't really care?
I think it makes sense.
Yeah, so this is binomial. So this is going to be n plus m. Choose m because k is m. P to the power k is m. Q to the power n minus k. That's n. And then this one, n is what? N is the total number of realizations. So that's, remember, look at here. So if the total number is n is given to be n plus m. So that's the total number of realizations is going to be in some time t. So that's e raised to minus lambda t to the power m plus n over m plus n factorial. This is Poisson with parameter lambda t. Because remember the problem, look at here the problem. The original Q is Poisson with parameter lambda, and we are looking at some up to some time t. So this will be lambda t with. So the number of the probability of the number of arrivals equal to n plus m is given by this one, this expression. So let me simplify this. I'm going to do it here. So probability of y equal to, I'm just using I'm just going to take the last. If you want to take a screenshot, take it. No. Yes. You got it?
Yes.
Okay. All right, so let's a probability of y of t equal to m, z of t equal to n is n plus m factorial, n factorial, m factorial, p to the power m, q to the power n, e raised to minus lambda t to the power m plus n over m plus n factorial. This cancels. So I'm going to write this as so notice that I can introduce here P plus Q if I want. So I can write this as e raised to minus P lambda T. Then you have P lambda. So P lambda T to the power M over M factorial e raised to minus Q lambda T. Q lambda T to the power N over N factorial. So what is each one of these? Anybody? What is this distribution? Huh?
Poisson distribution.
Both are Poisson. And what? So this is Poisson with parameter lambda pt. This is Poisson with parameter lambda qt. So what is the more? Look, the joint distribution is the product of the distributions. What do you call those random variables to be? Anybody?
Independent.
So this is a major theorem in queuing theory. If you have a Poisson queue coming in, and if you generate two sub-queues randomly, the key is random here, then each of them are Poisson with the parameter whatever is that randomness. So of course you generate three random queues, all of them will be Poisson. But the total thing, if you add this and this, you'll get back this. So in other words, you are sort of, the traffic is being split up. Remember, earlier we studied that Poisson plus Poisson is Poisson. Here what it is saying is, if you randomly split to Poisson, it is also Poisson. There are more properties. I'm going to stop with the Poisson here. I hope you understood. So we went through mean, autocorrelation function, and I gave you one property of the Poisson process. So you probably will study more when you pick up queuing theory, or I can, if we have time, I'll come back later.
Theory.
If you want a screenshot, take it. I'm going to move it on. Yes. Okay. Are you done?
Yes.
So this is another example. I'm just going through different examples. This is your homework problem also. One of the homework problems will ask you. And the Poisson process, by the way, there are videos on it. I think I forwarded it to you. So independent videos from YouTube, I already put you the link. So if you missed it here, you can watch it there again. So let's consider this process. See, random walk is like this. You toss a coin. If you get P, you take a step forward. A step is S. If you get another P, you take one more step. If you get tail, you go minus S. So I'm going to call this to be Xi, the outcome. So Xi could be plus S or minus S, depending on the outcome. You get head or tail. You toss a coin and then you go. So probability of Xi equal to head is P. Probability of Xi equal to minus S is Q. Probability of Xi equal to plus S is P. Probability of Xi equal to minus S is equal to Q. So what we are interested is, we want to look at the cumulative after some time. Remember, this is during delta, another delta, etc. So let's say we are here. So you took n steps, so that's n delta. I'm going to call it T. or n is t over delta. Delta is the step time it takes, a time for one step. I hope you understand what I'm trying to explain, right? On a duration delta t, you make a step forward or backward. If it is two-dimensional, you can take the walk in any direction. Three-dimensional, you can go into 3 dimensions. Let's just do 1 dimension. So I'm going to call it x of t. And actually what we want is we want to find out the process of this when delta goes to 0, s goes to 0. I'll come to that in a second. So you understand, we want to know where the person is and what is the autocorrelation function. So let's find out the expected value of x of t is expected value of xi. Let's say, I'm going to assume that the steps are equal size. So if the steps are equal size, what will be expected value of xi? Anybody? Look at here, xi takes 2 values. It takes s with the probability half. It takes minus s with the probability half. So the mean value is? Hello? Yeah, 0, right. So let's find out x of t1 comma t2. Remember, it is steps, so we no need to take complex conjugation here. So this is summation xi, I equal to 1 through t1 over delta. This is summation xj, j equal to 1 through tj over t2 over delta. So anybody, x1 is with all this, t1 is here, let's say t2 is here. So do you see that this can be written as yes, is this clear? Because if you expand here, you have this and this. So this together with this, you get a square term from here, then you get xi, xj. What is the expected value of xi, xj? Xi corresponds to here, xj corresponds here. So what will be the expected value of these terms? Anybody? So this will be expected value of xi multiplied by xj because these are independent. One random xi is from here, xj is from here. So they are independent because each step is independent. So this will be 0. So this will simply turn out to be xi squared. We can find out expected value of xi squared is going to be s squared multiplied by half plus minus s squared divided by half. And the whole thing there are t1 over delta. So this will be s squared over delta multiplied by t1. Do you see this? Let me call this to be a constant. So you can see here, let me go to the limit. Delta goes to 0, s goes to 0. None of these contributions will change, except alpha will be when limit delta goes to 0, s goes to 0, alpha is what? S squared over delta. So I will assume that s is, all I'm going to assume is the step size is roughly proportional to square root of delta, so that this is some constant alpha. Okay, so that's the only assumption. So I hope you see this. In a random walk, when the step size becomes extremely small and the speed with which the duration is extremely short also, then that limiting process is called a random walk. So the random walk has 0 mean and autocorrelation is this. So an interesting property is a minimum of t1 comma t2 from what we learned is a non-negative definite function. So your job, I think the homework one, let me see whether I have it here. So your job is to show that this is, so let me call this to be R of T1 comma T2, this one. So your job is to show that now, so how do you show this? This is what you have to show. You don't have, there is a video on this, precisely this problem. I have solved it. So just go through that video and copy the steps. So on minimum, how do you prove that this is true for autocorrelation function? So in other words, what you have to prove is the following. You have to create an autocorrelation matrix. Here the minimum with this ijth entry will be minimum of ti comma tj. Then you have to show, as somebody said, A transpose A is non-negative for any A. This is what you have to show. So this is your first homework. So you already know this is an autocorrelation function because this is the autocorrelation function of a random walk. I'll come to the, so as I said, go to YouTube, or maybe I put it already in your videos. I am not sure, but if you type in, let me see. If you type in minimum of yes, there is a video called Autocorrelation Function minimum of T1 comma T2. So that goes, if you go through it, the proof is given there. I'm just looking at it. So you are not going to do it. I mean, you may be, but you may or may not be able to do it directly. But at least if you look at the video, you will see you can just copy the steps. But that way, hopefully you can understand it also. So that is homework number 1. And homework number 2, we already did this in class right now, the first one. All right, problem number 2. So let me introduce one more concept. What is the time now? 4:46. All right, so I'm going to introduce the any questions before I move on? So your job is, so for example, I'm going to ask you, so you can, one way or the other way, you can answer yes or no. I'm asking is maximum of T1 comma 2 an autocorrelation function. Minimum it is because I showed you it is. So this is a question, I'm going to leave it to you. So let me introduce one more concept, then I'll solve you one homework problem and then we'll stop there. So a stochastic process is characterized by all these different realizations, each of this corresponding to values of psi i's. This is time here. Now suppose I take a set of random variables at time instance t1, t2, tn. I'm going to call this t1, x1, x2, xn. This is ti. So xi means x of ti. Now what I'm going to do is I'm going to shift all of them. So remember there, the joint characterization of these random variables is through their joined density function. corresponding to time instance T1, T2, etc. T1. This is the joint characterization of these random variables. So these random variables are characterized by this joint density function. Here this X stands for these random variables, X stands for the random variable X1, X2, etc. I just wrote a notation, okay, vector X. But this is a 2n dimensional function, X1 through Xn and T1 through, they all depend on T1 through. Now I'm going to move everything by some time instance C. So I get the T1 is moved to T1 plus C. Similarly, T2 is moved also by T2 plus C, etc. Everything is moved by C. So Tn is moved to Tn plus C. So the idea is that what if I look at the same random variables, but I come back tomorrow and look at them. So I will get a new, so I'm going to call them X1 prime, X2 prime, Xn prime. Xn prime means X evaluated at T1 plus C. I hope you see what I have done. All I have done is I've just shifted. And they will have their own, I'm going to call it X prime, X1, X2, etc., Xn. But the time instance T1 plus C, T2 plus C, etc., Tn plus C. So I shifted, if I shift all the random variables by a fixed amount, C, in other words, this is today, this is tomorrow, the same set of random variables. This is 8 a.m., 9 a.m., whatever, noon. This is 8 a.m., 9 a.m., noon, tomorrow. So the question is, so generally you expect these two density functions to be same or different? Anyone? Hello? What do you expect?
Different.
Huh?
In general, it's different.
In general, it is different. But if they are same, then we say that the process has got some stationary behavior. That's
Strict
what
stationary.
I'm going to come to that. So if the density functions are the same, we call it, you are right, strict sense stationary. So for a process to be strict sense stationary, this should be true for any n or for all n. It should be true for n equal to 1, n equal to 2, n equal to 3, etc. So first order strict sense stationary is means fx of x comma t is the same as fx of x and comma tomorrow. So instead of t1, I'm going to call this. This should be true. For NSC, remember here, this is true for all n, all c. It doesn't matter how much you shift. The joint behavior here and here should be the same. So this c here, there is a c here. The c should be the same. I mean, the c can be any value. So these two density functions must be true for any c. So what if I take c to be minus t? Then the first order density function will look like this. So what it means is, what does it mean? That means a first order strict sense, if a process is first order strict sense stationary, then the density function doesn't depend on time. You see this? Hello? There is no time here because it should be true for any c. So c equal to minus t, it should work. So this is true. I'm going to write like this. Generally, strict sense stationary is noted by SSS. And so consequently, now if you look at expected value of the expected, this is going to be x multiplied by the density function, fxx dx. So that's just going to be a constant. There is no time here. So if the process is first order strict sense stationary, then its density function doesn't depend on x. And one property is that the mean is a constant. So this is one property. Now let's look at second order strict sense stationary. That means if you have T1 and T2 here, And if I shift it by T1 plus C and T2 plus C, it's the same shift. This is T2, let's say, T2 plus C. Then the joint density function here must be the same as the joint density function here. This is what we mean by second order Strickson stationary. So let me put a C equal, this should be true for any C. Let me put C equal to minus T2. Then this becomes Fx x1 comma x2 T1 minus T2 or T2 minus T1. Either way, the difference T1 minus T2 tau. So this is the second property. If the process is Strickson stationary, then the joint density function only depends on T1 minus T2. So if you look at their autocorrelation function, remember generally it is T1 comma T2. That's going to be expected value of xt1, xt2. That's going to be double integral x1, x2. We can substitute this density function goes here, f of x, x1, x2, one variable, tau. It could be t, depending on what. We can put t2 minus t1 or t1 minus t2, dx1, dt2. So this will turn out to be a function of t1 minus t2. Rxx tau we can call it. Tau is t1 minus t2, or depending on which way we put, or t2 minus t1. So this is property 2. So what is property 1? If you want to take a screenshot, property 1 says if the process is first order Strickson stationary, then its mean is a constant. Property number 2 says if the process is second order Strickson stationary, its autocorrelation function only depends on T1 minus T2. So for a first order and second order Strickson stationary processes, property 1 and property 2 are automatic, follow as consequences. So properties 1 and 2 are consequences of Strickson stationary. In other words, Strickson stationary means properties 1 and 2 are true. So we can use the properties to define another kind of stationarity. We will use them as, we'll say that if properties 1 and 2 are, then we will call it wide sense stationary. We'll denote it as WSS. So if a process is wide sense stationary, if first expected value of x of t is a constant, not a function of time, and second, the autocorrelation function of t1 comma t2 only depends on tau, where tau is T1 minus T2 or T2 minus T1. So, so if a process is wide sense stationary, these two are true. But these two are already true if the process, so I have this, if a process is Strickson stationary, the properties 1 and 2 are true. So wide sense, it is strict sense stationary. But this won't be true if it is just a mean and autocorrelation or properties that doesn't imply anything on the density function. So this is the theorem. Now, if you look at the examples we have done, a minimum of T1 comma T2, the random walk, is it stationary or is it stationary of any kind? Anybody? Hello?
Poisson?
Poisson, is it stationary any kind? Look at its autocorrelation. What is its mean?
It's lambda t.
Yeah, so is it Whiteson stationary or no?
No.
And look at its autocorrelation function. It's not a function of T1 minus T2, right?
Yes.
So it is not Whiteson stationary. Yes?
Mm-hmm.
Yes or no?
Yes.
How about, is it Strickson stationary? Look at there. Look at the. Look at my last slide. If it is all Strickson stationary processes are Whiteson stationary. Yes.
Yes.
So if the process is not Whiteson stationary, it is not going to be Strickson stationary. Yes.
Yes.
Okay. Very good. How about the last example? Wiener process. Anybody?
Which process?
The random walk. The autocorrelation was minimum of T1 comma T2, right? The autocorrelation. Remember, minimum of T1 comma T2 is not a function of T1 minus T2. Yes?
Yes.
Yeah, so is it Whiteson stationary or no?
No.
No, right. But if you look at that cosine of omega naught T plus phi, we got the autocorrelation function to be omega naught multiplied by T1 minus T2. So that's a Whiteson stationary process. Now the Wiener process, the random walk is, a limiting case of random walk is also known as Wiener process. In other words, the step size is small and the steps are done very fast. So that's the Wiener process. And Wiener process is this one, x of t, limit delta goes to 0, s goes to 0, sigma xi, I equal to 1 through t over delta. So we found that its autocorrelation function is alpha multiplied by minimum of T1 comma T2. So this is not stationary. So definitely not Strickson stationary. But look at here, you're adding a large number of random variables. So you can say this is a normal process. So how do you get its a normal process? We already know its mean is 0. How do you find its variance? Anybody? If the mean is 0, what's the expression for variance? Anyone?
It's here.
What is the expression for variance if mean is 0?
Just x square, expected value of
X squared t, right?
Yes.
And look at here, x squared t means what? Rxx, t1 t comma?
T comma T.
Very good. So that's here. You put a t1 equal to t2. What do you get? Alpha?
Alpha T.
Alpha T, yeah.
All right, very good. So you should keep this in mind for, let's look at the next homework problem, number 2. Do you have it there? Look at homework 8, number 2. Do you have or no? Hello, can all of you look at homework number 2? Homework number 8, problem 2.
Yes. Yeah.
Yes, Professor, we are looking.
Oh, read it to me.
Yes, Professor.
Read it to me, please.
X of t equal to
X of t equal to
e raised to j in bracket omega 0 t plus W4.
W4?
It's WT.
What is WT?
It's a Wiener process.
Wiener process. We just went through it. Look at the previous step. Wiener process, what is the mean? Anybody? I just went through it.
0.
Mean is 0. So it's a normal process with the mean 0, variance x of t, alpha t. Okay. So WT mean is 0. Variance of WT is alpha t. And WT is a Gaussian process. Mean 0 alpha t. So I'm not going to completely solve for you, but I'll give you clues. So you find, well, the question is, calculate the mean of x of t. So the mean of x of t is x of t. That's e raised to j omega t is a constant. So e raised to j omega naught t, expected value of e raised to j w of t. So now you can see the value of characteristic function. So go home and start thinking that way. See, this is w of t is a Gaussian process with the 0 mean and variance this. So anybody, how do you compute this quantity? Anyone? What will you do? How are you going to get through this course if you can't even do this? You already forgot?
Take the integral.
Not integral. What is that function? Look at, we learned this. We learned this. How is this related to this?
It's the characteristic function.
Yeah, characteristic, because there is no omega. So this is the characteristic function of this random variable, which is x, evaluated for what value of omega? Omega is 1 here. 1, right? So you look at the characteristic function of the Gaussian and plug it, and then try to do the autocorrelation function and see that. Let me not do the whole problem for you. So the theorem is, before we stop, let me do the theorem. And the third question is, I'm going to solve it now, theorems. So what we have shown is strict sum stationary leads to wide sum stationary. But I said in general, this is not true. So there is an exception here, except when x of t is Gaussian. So the way, why for Gaussian, say let's say x of t is Gaussian. I'm going to show you this proof quickly. Then we'll start the exam. Sushant, are you there?
Yes, Professor.
So in about 5:12 or something, as soon as I finish, you can send them the exam.
Okay, yeah, Heifeng is gonna send them. Okay.
I know. Is he there or no?
Yeah, I think Heifeng is
I'm here.
also.
I'm here. I'm here.
Yeah, I'll let you know. Let me finish this.
Yeah.
So if x of t is Gaussian, take a set of random variables x1, etc., xn. Remember, it's Whiteson stationary Gaussian. So it's autocorrelation Rxx ti comma tj only depends on Rxx ti minus tj. So let's find the joint density function of x1, etc., xn, x1, etc., xn, corresponding to time instance t1, t2, tn. We want to show that if this is true, we also take the joint characteristic function of at time instance t1 plus c, t2 plus c, etc., x1, etc., xn. We want to show that these two are equal. That's what we want to show. If we can show these two are equal, then the process is strict and stationary. So listen to the proof. I'm starting with this side. I'm saying x of t is Gaussian and Whiteson stationary. I'm going to show that from here you can come here, except when it is Gaussian. So let me take Gaussian and Whiteson stationary. Then I want to show this is true. Or equally, you can show the characteristic functions. Take the characteristic functions omega 1 through omega n. I mean, maybe we don't have to do. Now, if you do the, so this is the thing I'm just going to tell you. The joint density function will turn out to be e raised to minus x transpose the covariance matrix inverse x. So the covariance, here also the same formula, except this covariance matrix, if you expand, this will be R of Ti comma Tj. And here, let me see where the, right. So remember the Whiteson stationary property is the autocorrelation only depends on Ti minus Tj. So the whole point here is we did it for 2, some constant. The joint density function for n random variables will involve the inverse of the covariance matrix, but the covariance matrix consists of Rti minus Tj. But if it is Whiteson stationary, Rti Tj is R of Ti minus Tj. If you go here, it is exactly the same thing. You have X transpose R inverse X. But this R is R of Ti comma C, Tj comma C. Because of this, we are taking time instance T1 plus C, T2 plus C, etc. But because it is Whiteson stationary, this will be the difference of these two time indices. So this will be also Ti minus Tj entry here. So look at this. This entry and this entry are the same. That means this will be actually equal. So if we can show the two density functions are equal, then we get a Strickson stationarity. So starting with the Whiteson stationarity and Gaussian, you get a Strickson stationarity. That's the only exception. So remember, we went over all, actually we didn't cover much. So I gave you the characterization of the stochastic process is through first order and second order density functions and their mean values and autocorrelation functions. And then I gave you 2-3 examples, including Poisson process. Poisson process, then I introduced the concept of stationarity, both the Strickson stationary, Whiteson stationary. So I hope you see this theorem. If the process is Strickson stationary, it's always Whiteson stationary. So if the process is not Whiteson stationary, it can never be it can never be Strickson stationary, because for it to be, at least it need to be Whiteson stationary for it to be Strickson stationary. So if you know a process is not even Whiteson stationary, then don't even think about the Strickson stationary, right? So one exception. So generally Whiteson stationary doesn't give you Strickson stationary, except when X of t is Gaussian. So Gaussian and Whiteson stationary is the same as Strickson stationary. Okay, I'm going to stop here. Anybody has any questions? And we'll pick it up from here next week.
Professor, I'm leaving this session and going to the online session.
Yeah, you go and you can, Hifeng.
Yeah.
Yeah, you can also send the, what do you call, start giving the exams now.
Okay.
So I'm leaving the meeting right now.
Okay, very good. And the students, all of you have, Hifeng, if students need to put in their cameras now, we are going to go through, and if your camera is not on, then you will not be, I'm not going to take into consideration. So keep your cameras on, please. If anybody doesn't get an exam, just tell us, then we will make sure you have it. So remember, the exams are not the same. There are multiple exams going on. So please don't try to ask anyone. You only have limited time. We are going to close that thing at 5:45. I mean, you can post that thing at 5:40. What time is it? You already sent it? All right, so why don't you close it at 5:50? No, that's fine. When everything, I'm going to wait here. When everything is done, you call me back. You have to also monitor them, right? So when you are done with the exam, you can upload it and go and get out of it. Yeah, what time you are going to close the exam? What time will you close the exam? 5:50? That's fine, yes. Yeah, that's good. And keep an eye on all the cameras. You're looking? Okay, very good. Students, please do your homework. I mean, your problem, because your friend's problem will be different. Remember, you can look at your books because there is no, but please don't waste time talking to other people. It's not going to help you. So next week I'll go to maybe 2 random variables on the test. One function of 2 random variables.